Okay, let's begin. Alright, I think I left the quizzes when I went to. Let's find the electronic version. Let's quickly go over the quiz. It'll be a little bit of review as well. So let's find that. I guess I'll go over version A. Version B is similar. So this is version A. So we have a surface that's, so this is problem 1, we have a surface that's parameterized by R of ST. What's the formula for the normal vector?
RS cross RT.
Partial with respect to S, cross product with the partial with respect to T. That was that answer, so 2. Find a vector function for the rightward pointing normal. So here's y equals minus x squared minus z squared. I want a normal vector that points to the right. And by points to the right, I mean in the general setup of how we use the axes. So that's your x, your y, and your z. So I want a normal that points generally in that direction. Right, so your textbook sometimes describes up and down and right and left in terms of that sort of setup. So how do you go about it? How do you find the normal to that guy?
So it has been normal vector has been negative 2x, 1, negative 2z.
And it would be minus 2x.
And 1 and negative 2z.
Positive, right?
How did you get that?
What's the name of the formula?
What formula? Like, tell me how you got to it.
So partial derivative, okay.
What? How do you get the answer?
Partial derivative of x
So you use partial with respect to x?
and put a negative sign in front, and then so since you are doing it to the y would be constant 1, and then partial derivative to the z and negative.
Okay.
Yeah, that's it.
Does that match with this?
No. It's positive.
Because it would be positive.
Wait, for my one it was positive, no?
Oh, you probably had the other version. Okay, it's probably okay, but that's this one. Okay, so this in this case that would be positive. Now,
Yeah,
is that the one we would take? Is the question. Is that the right pointing normal or the left pointing normal? How would you know?
Unoriented surfaces and all pointing out are your normal vectors.
Well, we didn't talk about oriented surfaces yet, but this vector, does it point generally in the right direction or the left direction? How would you know?
It's a vector, right? So
Yeah, I know. So how would you know if that's pointing in the right direction?
positive slope. Positive slope.
If you just
What
put,
means a positive slope?
No,
put a
There
test
you go,
point,
that way.
It's in 3 dimensions. There's no
No.
positive or negative slope.
just
Professor,
put a test point like x is 0 and z is 0, then you'll see that at the apex it's going to be pointing towards the right.
don't you take the curl of the vector
You
that
guys
If
are
you literally just saw
way too
one,
complicated. Okay, just look at that guy. Look at the y. It's a positive 1, so it's pointing to the right. Right? Positive means in the y direction, you're moving to the positive y. So it means your vector is, as far as the y-axis is concerned, you're moving that way. If, for example, you did this formula, but you wanted the left one, you wanted the vector that pointed that way, you would just take the negative of everything, right? So there are times when the vector that you get by using the generic formula is not exactly pointing in the right direction. And there's going to be a time when the orientation of the normal vector is going to be important. That's why I want you to get used to the fact of not just using a formula and getting to the normal vector, but you need to know that the normal vector you're using is pointing in the right direction. Not every circumstance would require that. In any case where you need to find the magnitude of a normal, it won't care. But there are times when we actually care about the direction in which a normal vector is pointing in. So for this one, if I want to point to the right, it means I need the y-coordinate to give me a positive number. And so I would use the formula that has the negative here, positive 1, and a negative here. And therefore, this would be the correct normal vector. If the question asked for the leftward pointing, the answer would be the negative of this, right? You would have to know to take the negative. But yes, this is the nice form that you can use when you have one variable solved for in terms of the other variables. What's the next question? Okay, S is the open cylinder. So this is problem 3. It has 2 parts. S is the open cylinder given by y squared plus z squared equals 4. Your x is between that and that. Can you describe what that looks like?
Should be a cylinder
Yeah.
with respect to the x-axis.
Okay, so it's running along the x-axis, right? Okay. And it's between x equals 1.
And
So there's a circle here where the center is 1 and x equals 2. So your object looks like this. Right, you weren't required to sketch the object in this case, but eventually sketching will be very useful, so we should at least have an idea of how to do it. So that's the kind of object we're looking at. Okay. Now the question asks us, parametrize S. How do you parametrize S?
So x would be r cosine theta? No.
So let's say, come on, like u and v or something similar.
X is V.
You'd say x is v,
Yeah.
and
U would be cosine.
3 through r, 4.
2 cosine
Cosine.
U.
u
Two
and
sine.
2 sine. Anything similar to that? The limits? What would be your v limits? What would be your u limits?
V would be 1 to 2.
V is just the x value, so it's just going between 1 and 2, and the u?
0 to 2 pi.
0 to 2 pi, because that would give me the full circle in the yz plane. So that would be the parameterization, or anything similar. You could use a and b or s and t.
Could you use
I would
theta?
also accept you switching the cosine and the sine. That's fine at this point.
Professor, could you
Yeah.
use theta instead of u?
Yes, as I said, you can literally use any variables here, except the x, y, and the z themselves. For v, you could use literally x itself, but you don't use the y and the z again.
In
Yeah.
general, does it matter if you switch the sine and cosine when you have a cylinder?
Yes, it will matter in cases where the direction that you're traveling in matters.
Okay.
Remember, there will be cases where the orientation, the direction in which we're moving will matter. And so you should remember that if you're going around a circle, and if you choose the x to be the cosine and the y to be the sine, you move counterclockwise. Whereas if you switch them, you move clockwise. So by switching the cosine and the sine, you're changing the direction. It just so happens, by parameterizing the cylinder, I don't really care what direction I go around it. Ultimately, if I take all these points, I will create the cylinder.
Can you write x equals to v?
Oh, you mean as a set of parametric equations? So yeah, you could, another way to write this answer, you could list the equation. You could say x equals v, y equals 2 cosine u, and z equals 2 sine u. And write that list of equations down, that also works. Let's see.
And I said x equals to x, and then 1 to x to 2.
Yes, you can use any letters.
Okay.
Okay, so the next one was find a normal vector to S. So assuming we're going with this u, v thing, how would the normal vector look? So this was part A, to parametrize. So this is 3b. How do you find the normal vector to S? And it says a normal vector, so I don't particularly care what direction it's pointing, just find one of them. What would you do?
So wouldn't it be 1 to negative 2y and negative 2z? That's the normal vector for this.
If it, you're asking me if it would be 1, negative 2y, negative 2z? Is that what you're asking me? Oh, no. Why is that not the answer?
Because
It's
parametric.
Yeah, but even, let's say you wanted to use a shortcut formula here. Why does this not give you the right answer? What's something that you can just immediately see that can't possibly be the answer?
X is not 1.
Huh?
X is not 1.
The 1 is a dead giveaway that that cannot possibly be the answer. Why?
it will be 1 to 2.
Because it's supposed to perpendicular with X.
It's supposed to be perpendicular to this surface, which means your normal vector is going to point straight up. Now if it's pointing straight up, according to the x-axis, what direction is it moving in? 0, right? Because a positive number would mean you're moving this way, a negative number would mean you're moving that way, but you're moving straight up, you're not moving. Which means your normal vector in this question has to have 0 in the first coordinate. Which is why that formula will not work. And that's sort of something that should tell you that the formula would not work. Besides the fact that, you know, this is in parametric form, so you probably wouldn't use that formula anyway if you went through the trouble of parametrizing it. So how would we find the normal vector if we can't use
Cross
the formula?
product.
Huh? Do the cross product. Do the definition that you did in problem 1. We know that the normal has to be the partial with respect to u cross product with the partial with respect to v. So that's what I'm going to do. So find r sub u. This would be what?
0, negative 2 sine 0, 2 cosine of it,
And r sub v.
1, 0, 0.
And now we're going to take the cross product. So we're going to set up that ijk, and our n is going to be that result. So I'm going to cover this up.
0.
0 times 0. So we get 0 in the first coordinate, which is expected. Cover up the middle one. 0 minus 2 cosine, but you change the sign of that, so that's 2 cosine. And then you cover up the last one. 0 minus a negative 2 sign using positive 2 sign. So that would be the normal vector. Or you could have the negative of this, it would be the same. Right. It will be negative if you took these cross products in the opposite order. So yes, that formula I gave you, it's a shortcut and it's nice to use, but it doesn't always apply. You have to be very careful how you're applying it. And you should, again, remember how vectors work, what it means to have a positive number in a coordinate. It's telling you about how you're moving. Right? If you have a positive number in the x-coordinate, you're moving in the positive x direction. If there's a negative number, you're moving in the negative x direction. This normal vector is moving in neither direction. You cannot have a non-zero number in the x-coordinate. Okay, let's talk about here. Okay, tangent plane to this surface. So we're given a surface here. It's parametrized as u, v, u squared minus v squared. And I give you the point that I wanted to parameterize at 2, 1, 3.
For this one, you will find the RU respect to the RU, and then so that would be 1, 0, 2U, and then RV, RV. So that one would be 0, 1, negative 2V,
Then?
and then you take the cross product of those.
Are
You could, but I wouldn't.
Why not?
Because it would be easier to just plug in the numbers right away. Like I know the point I'm at.
Yeah. So you know that u equal to 2 and
So I know that
v
u equals 2
2
and v equals 1.
1.
I would plug those in right away. If I know the point,
Uh-huh.
getting the general formula is usually going to be more complicated because you have to do this. But if they're just numbers, it's a lot easier to actually get to them. So I would right away, if I know where I'm supposed to be, there's a difference between finding a normal vector function in general and finding a specific normal at a specific point. I'd sort of get rid of the variables as soon as possible. So at this point, for this guy would suggest that u is equal to 2.
2.
V is equal to 1, so I'd immediately plug in u equals 2 here, so this guy
Would be
would really be, I'm looking at 1, 0, 4.
4. And
Here I'm going to plug in v equals 1, so that would give me 0, 1, minus 2.
Uh-huh.
And these are the two guys that I would cross product to get the normal.
Oh, okay.
But yes, you could cross product these in general and then plug in u and v afterwards, but computationally it'll actually take you a little bit longer to do that. So then my n now is just going to be the cross product of those two. 1, 0, 4, 0, 1, minus 2. 0 minus 4, this is minus 2 plus 2, 1. So that would be my normal vector. Or the negative of that.
And then it would be negative 4
What was the
times.
question? To find the tangent plane?
Yeah.
Okay, so we know that the tangent plane formula is going to look like ax minus epsilon plus by minus 41 plus cz minus 7 equals 0, where the a, b, c comes from the normal vector, so that would be minus 4 times x minus the x coordinate plus 2 times y minus the y coordinate, and 1 times z minus the z coordinate. And that's your tangent plane.
Can we use the other formula with the t and s? Like the initial point plus t vector u and s vector v.
Coming in?
The
For
initial
the,
tangent plane,
oh, you mean the parametrized form?
yeah.
Yeah, you could use that. So a parametrized form would be something like, if you parameterize it, let's say you said you want to use S and T.
Uh-huh.
You could plug in the point, which we know is 2, 1, 3, plus t times one of these, plus s times the other one. So it depends on what form you want it in. But usually the scalar form would be more useful, but that's also an option. Was that it? Now for a smooth surface S parameterized by R of ST, this is the last one. So here my S, again, I parameterize by R of ST. Find a formula for the surface area of S over D. So I'm assuming the points ST lie in some domain D. What is the formula for the surface area?
The integral cross, can you do cross R S R
U.
and magnitude?
It's the magnitude of that.
dA.
So it's the magnitude of the normal dA.
Professor,
Yes.
would that be work if instead of R U for my one it had U and V?
You have another version, so the
So-
variables used might be different.
Okay, so instead of putting R S cross R T, would it be okay to put a magnitude of the normal vector, which is the same thing as
Meaning to just write this?
Yeah. Would that be work? It's the same thing.
What did the question say?
Just to specify the things that are not defined.
Yeah, so it says if you use any symbol not in the question, define it. Which means if you use n, you would have to add a sentence telling me that you know how to compute n and say what n is.
Okay.
So you can say where
N
n
is
is r
cross.
s cross r t, or tell me some other way. Say n is the normal vector, and this is how you compute it based on those variables. Does anyone know how to define this guy?
Double integral.
So this is the bonus. We haven't covered it yet, and at this point we're not. We probably won't get to cover it. But
Is it like flux?
Double integral d.
that's not the flux. But
It's
it's called a. This is called a surface integral over a scalar field.
Double integral d f of r of u v. F of r u v.
And then the
Magnitude of the
that
cross
normal.
of rs and rt.
Times the magnitude of the normal.
dA.
dA. That's called a surface integral over a scalar field. That will be
13.7.
That's in the next section. That's 13.7. The other one.
Wait, we get one right with 1 point, right?
Yes. What's this one?
So this one will be a double integral of s and then f dot n ds
F of?
will be n. N is a normal vector now.
Are you cross RV?
Well, you have to plug in the parameterization. Again, we're assuming you're parameterizing here. So you can plug in the parameterization into the f, and then what do you do? So you get a vector function.
You dot it with a normal vector.
You have to dot product it with a normal vector. Not the magnitude. D8. So here you're multiplying by the magnitude of the normal vector. Obviously in this case, the direction in which you're moving won't matter. So it doesn't matter who's negative or who's positive, or if you put the sign in the second place or the cosine in the second, it's not going to matter for this guy. For this guy though, you're dot producting with a certain vector, which means if your sign is off, the answer is going to be off. This guy cares about orientation, he cares about direction. This guy doesn't. These are kind of like a higher dimensional analog of the single integral ds integral, where you're taking with respect to arc length, you actually didn't care about direction. This is sort of a higher dimensional analog of f dot dr, in which you did care about direction. Right? So for this guy, it's going to be, you need to know, is the normal vector pointing to the right or to the left or up or down? It's going to be an important consideration for this, to complete this integral. It's not an important consideration for this integral. This one, yes, is also what's called the flux. Right? And we'll talk about that when we get to it, and what that actually, how we interpret that physically. But that's 13.7. We still have to wrap up on 13.6.
I have a question.
Yes.
How do you think we should best prepare for your quizzes? Because I've been trying to do the homework, and it's like, the homework is so hard compared to everything else. Like, do you rather we do the ones in the book that you suggested? You get what I'm asking?
Oh, yeah, the suggested problems in the book are always nice to do.
Yeah, but it's like, then we have like the homework problems that are like so hard compared to everything else. So it's like, what should we focus on for the quiz? Just do prepare by doing the ones in the book?
Well, let's think, like, what do my quizzes usually look like? What are the kinds of questions I usually ask?
Formula.
Theoretical.
Huh?
Theoretical.
What?
Formula.
Formulas. You'll notice that in every single one of my quizzes, I ask you, here's this idea, tell me a formula that computes it. So that's one thing you need to do. So obviously if you want to do it on the quiz, you know I'm going to ask you about a formula at some point. You need to know the formulas for all the things. that I will be talking about. So pretty much anything I write in a box, you're going to need to know. What else do you think you need to know based on the pattern? I mean, we've had 6 quizzes so far, so hopefully you guys are paying attention to kind of the kinds of questions I would ask. Well, what else do you think I would ask about? So let's say you're doing a homework problem.
One of the
And it
questions.
Takes you like 2 pages back and front to do that homework problem. Is it likely that that homework problem is going to show up on a quiz?
No.
No. It's going to be a very short thing that you can write a short answer in, and I'm assuming that you're either going to have like 1 sheet of scrap paper, or you probably even use the back of the quiz. So it can't be super long. So it has to be something that you can compute that is very important, usually using the formula. You'll notice that I asked you about a formula in problem 1, you use that formula in future questions. So not only do you have to memorize the formulas, but you have to actually know how to use them it can be challenging problems, but it won't be a long drawn out problem. So if you would probably go from the homework, which is testing you on more than just being able to rapidly compute a bunch of things, you can actually look at just, okay, so here's a concept that this homework introduced. What are the main formulas? What do the symbols in the formulas mean? And how can I apply that to solve a quick problem? Right? So if you learn about so if there's a homework that's focusing on the f.dr integral, what you should take away from that is, what's the formula to compute that? How can I compute that for a random question? Right? So if I was told an f and I was given a curve, could I compute f.dr? So those are the kinds of things that I want to talk about. So basically, the homework is more of an exploratory kind of thing, where you're really kind of using concepts to some larger goal. But on a quiz, I'm really testing you about the essential things. Do you remember the formula? Can you apply this formula? That's the sort of thing that you want to do. And if that's your goal and you can't really figure out that from the homework, then yeah, you might want to go to suggested problems. But at the end of the day, just like with the things we're doing in general, like in math in general, you're always looking for patterns that you want to exploit. So yeah, even with this class, you should be doing that. What are the patterns that Jhevon uses? How can I take advantage of that to get an A? How can I force Jhevon to give me an A? What is he going to do? Sort of, you have to sort of take a game theory approach. Yeah, so if you look at all my quizzes, there is a pattern. There are certain kinds of things that I would ask, and you can almost predict the kind of question I'm going to ask you. So I'm going to ask you about a formula, I'm going to ask you to use the formula, and I might ask you to state what each symbol in the formula means. Right? Any other questions?
Professor,
Yeah.
I have a question about quiz 5A. You said that suppose, I need to show it to you. What's wrong with this? Like,
Oh, I do that later.
okay,
All sorts of things.
okay, alright.
Okay, so let's, where are we, 13.6. So again, let's summarize the essential ideas that we came across here. We spoke about parameterizing. Surfaces. What you need to remember, these were 2D objects, which means they have 2 parameters. Has general forms you can exploit. So basically, if you look at a cross-section, it's similar to how in that thing where I asked you to parameterize a cylinder. How you basically come up with that parameterization is figuring out that, oh, the cross-section is a circle, and so I can use sine and cosine. So they do have their general forms. You need to remember roughly what a circle would look like, what a plane would look like as a formula, and you can sort of apply that to this 2D case. But you need to make sure that whatever your parameterization is, there needs to be 2 variables in it, or it's not a surface. So that was just the main ideas there with parameterizing surfaces. We also derived an area formula if we're computing surface area. And what was that? well, that was the form we had before, so that was the magnitude of the normal dA. That gives you the area of D. Of S over D. So that basically is the situation where you have some surface here, that's your guy called S. Its projection in, for example, the xy plane is D. And so the area of S that's above D is given by this integral. So that was another important concept. We also covered the concept of finding n, which is our normal vector. Okay, so 1 was the main formula, right? Where if S is parametrized by two variables, let's say for the sake of argument they're called u and v, then my n is given by the cross product of that with respect to u and v. Now at this point we didn't really talk about orientation too much or what direction things need to be pointed in, but that should sort of be intuitive by what you know about vectors and how they describe a direction. There will be a point where I'll tell you specifically about what, we'll describe oriented surfaces specifically in the next section. And we'll talk about how you can make sure it's pointing in the right direction. So that's if, so this use if S is parametrized, or you have to parametrize. I mean, have to is a strong word, but there are some times where it's very compelling that I should probably parametrize in order to get that normal vector, which you kind of describe by this last one, is that the short formula below does not work. So there was a part in the quiz where we saw that using the formula puts a positive 1 in the x-coordinate. There's no way that could have been the answer because there had to be a 0 in the x-coordinate. So if you're, obviously you can just try to apply the formula, it would not work. Even though usually it would be clear because you wouldn't be able to solve for the variable to get it to work. Or you'd have to parametrize something because your normal vector is changing directions, like your surface is broken up into pieces where the normal vector for each piece would be different, as in the case of a sphere. Or if you're given a parameterization, you just use that parameterization and you compute that normal with this formula. The second one is if given S as a scalar equation, say you can solve for z and you get a function of x and y, then you can use the normal is minus respect to x, minus respect to y, positive 1, right? And basically you parametrized as x comma y comma f of x y and used formula 1. Right? So basically you did all the work for this guy, you went through you crunched the numbers for this situation, and this is your result. So it kind of saves you from doing a cross product if you know that this formula is just going to fall out right away. You can immediately jump to this once you have this situation. Okay. And of course, note the roles of the variables can change. So that means if you're given that x is a function of y and z, then you can use n to be 1 minus partial respect to y minus partial respect to z. Or if your y is a function of x and z, then you can use the normal minus fx 1 minus fz. Right, you can permute these. It just depends on what plane you want to project in. So if you're projecting into the xy plane, this is the normal. Projecting into the yz plane, that's your normal. Projecting into the xz plane, that's your normal. Right? You can swap who gets to be the 1. right? And obviously, if this is a positive one, you need a negative on those other two because we actually ran through the cross product and that's what you ended up with. But that was the basic idea. As I said, 2 will be the quickest way to do it. But sometimes the formula it doesn't work. You're not in the right situation for it, and so you might have to fall back on this. But this is really, in general, how it's done. So you really start here, and this formula was derived from that in the nice case where you can actually solve for one of the variables. So, since we don't have much time, I probably want to explore that idea a little bit more. Because it's going to be important moving forward when we get to surface integrals and all that stuff. And we start talking about oriented surfaces. Okay, so let's look at an object like this. So it's just an up to right cylinder versus, so this would be an example, say this is x squared plus y squared equals 4. And I could describe x squared plus y squared equals 4, but we define that x to be greater than or equal to 0. Or here, I could describe a sphere x squared plus y squared plus z squared equals 1. Or here, I could describe something like the upper hemisphere. X squared plus y squared plus z squared equals 1. Obviously the sphere is going to look like this. I just want to quickly make sure we take a sort of conceptual look at these. What would this guy look like?
Could be a cylinder respect to the z-axis.
Sure.
It's gonna get quiet.
Yeah, greater.
Huh?
X
It's gonna
could
be
be
half
greater
of it.
than 0.
Yeah, so what would that picture look like?
It's
How
gonna
would
be half
it
of
change this?
It's on this
Half of it.
So
It's just on this
the-
side.
Right.
So it's like half of this cylinder like that, right? And this guy is a full sphere. What would the upper hemisphere look like?
It just get cut in half at
So
the
we
right.
will cut in half.
Mm-hmm.
So
On the XY plane only.
C more than.
Above the xy plane, right? So you really want the top part of the sphere, right? Because that's what the upper hemisphere. Right? Now that automatically tells you a few things. Now in general, if I wanted to find the normal vector to this one, how would you kind of approach that situation? Method 1 or method 2?
Method 1.
Here, I would use 1. I would parametrize. Why?
It's not moving though. See?
Hmm?
Oh, the normal vector can be 1 because C is.
Right, the normal vector is pointing straight out, which means the z-coordinate has to be 0, which means using that formula that has the thing in terms of x and y, it would have either a positive 1 or a negative 1 in the z-coordinate, so using that formula would not work. So given this situation, parametrize is how I would do it. What about this situation?
Both variables.
would be formula 1. You have to parametrize.
Would you? we do understand what parametrizes would involve, right? You
Yeah.
have trig functions, you have to take the partials with trig functions in it, then you have to take the cross product of that. So yeah, I just wrote down the word parametrize, but it's a pretty involved thing. It's kind of something you don't want to do unless you have to. Do I have to do it here?
No,
No.
Give me an option, give me another option.
x equals to,
I can solve for x because I know the x is positive, which means I can take x is equal to the positive radical of 4 minus y squared. And so I can automatically know here my normal vector is going to be, now my x is the guy that I've solved for, so that guy gets to be the 1. I'll do the partial with respect to y, partial with respect to z. Right? Obviously the partial with respect to z would be 0 in this case. And so I just need to take the partial with respect to y of this guy, put it there. That's my normal. That will be a lot less work than going the parameterization route. What about the sphere? So here I would actually do option 2 because this little piece of information here gives me something I can use to actually write down a formula.
But then you said for the first case, you can't use the second option because the normal is parallel to the x-axis? Kind of,
Oh, yeah.
kind
Wait.
of like that?
Because the normal is parallel to,
The-
The z-axis.
it's not parallel, the z-axis is here. The normal is perpendicular to the z-axis. So it's not moving up or down according to z.
Oh.
The z coordinate isn't changing.
But isn't it the same in the second case?
no.
Sure, but that's if I'm thinking of this in terms of the xy plane. But here what I did was I projected into this rectangle. So I'm actually thinking of things in the yz plane here. So I changed my perspective. I solve for the x, which means I'm looking at it as a function of y and z.
Okay.
So it's not the circle that I'm now caring about, it's the rectangle that I project onto.
Professor,
Yeah.
what, I mean,
So if I'm even setting up the limits here, it would be the limits of a rectangle.
I'm confused for 1 and 2. It's still, so in 2 you solve for x and use the second formula,
Yes.
right? But why can't you, in 1, why can't you solve for x and use the second formula? Why do you?
Well, if I solve for x here, what would happen?
Positive and negative.
I would get a plus and a minus.
Oh, okay, okay.
So technically I could do that, but I'd double my work. I'd have to do one for the positive side, one for the negative side. And if my function isn't really symmetric, where it's not predictable how that will work out, I could potentially be doing 2.
Okay.
In that case, parameterization is the more efficient way to
Okay,
go.
so since this one is.
In this case, I was told this is positive, so I know the minus doesn't
Minus.
exist,
Okay. So
which
now,
now
we can do one
it's
of
easier
them.
to do the formula.
Okay, alright.
Yeah, I know that this can be confusing. That's why I keep going over the concept.
Okay. For this one, you need to no. Yeah, you need to parametrize
Yeah, whether you solve for x, y, or the z, again, you'll get 2
two
things.
things.
So that's one idea. So you probably wouldn't want to do part 2. I would go with part 1, parametrize. But I'm going to show you something neat about the sphere in a second. I'm going to show you something that you can get away with a sphere in a second. What about this guy?
Z has to be positive.
Z has to be positive, in which case here, I would actually solve for the z. And then I can use the formula. So this would be minus the partial with respect to x, minus the partial with respect to y, positive 1. So it's important that, computation is of course important, but it's important that you can also look at the situation you're in and know what's the most efficient way to choose. Because as you can see from the formulas that I wrote and from the bonus forms about surface integrals, the normal vector is just a part of the formula, right? After you find this guy, you're still going to have to set up a whole integral and compute something. You don't want to be spending a long time finding the n. So it's important that you can know the most efficient way to do it, and you can just sort of I can describe a situation, you can sketch the situation, based on your sketch, you know, this is the best way to find the normal, this is the most efficient way, and then that, you run with that, then you, afterwards, you set up your integral and all that stuff. You'll be doing that. So you're gonna be doing a lot of things at once. It's important that each individual part of that process, you're very efficient on that part. Yeah, very
But
much.
that one can't you do number 2, because like it's symmetrical above the xy plane, the sphere, right? So it's basically you do the second rule for the top part and then just negate the other one.
Not always. So remember, ultimately what we're heading towards is something called the idea of a surface integral. So it's not just going to be the area of the thing I'm on. I'm going to be integrating some other function on top of that surface. So if that function is not symmetrical on the top part of the sphere as the bottom part, then I can't use that. So while my ds is symmetrical, my function here can behave very differently based on whether I'm on the top or the bottom. So you have to be very careful with that. It could be the situation where, oh, I can just do the top and then the negative of that is the bottom. It could be the case, but in general, given if I give you some random function, that could not be the case, right? You could have some sort of, and this is just a crazy situation where once you're above the xy plane, your vector is doing something, while if it's below, then it's conservative, and so the bottom half is going to give you 0, and it doesn't matter what the top half gives you, right? There are situations like that. So sure, if you're integrating a constant, you can kind of do it that way. Just do the top, and then the negative of that would be the bottom. But the function that we're going to be doing more with just the surface. So you can't automatically know that's going to behave symmetrical. Depends on, remember, we're now in the kind of thing where our environment has stuff going on into it. So it's possible that in the bottom half of the sphere, our environment is doing something different from the top, and that can kind of skew our answer. Here's something cool about the sphere. The concept of a radial vector, which we can kind of figure out from this. So you can have this sphere, and so you want to compute a normal. And notice that once you're in the upper hemisphere, your z component of this normal should be positive, while if you're in the lower hemisphere, it should be negative. Right, so you can kind of have two different situations. But one thing you can notice is the following. Let's say I did the top. Right, let's say this is the unit sphere, x squared plus y squared plus z squared equals 1, for example. And I parametrize the normal vector for the top. What would it look like? Well, not parametrize, just find the normal. I could solve for z, right? I get the radical of 1 minus x squared plus y squared, right? And I could use minus fx minus fy positive 1. What would that look like here? So the top means I'm setting z equals to the positive radical of this. So this guy would give you what? Something like x over that? Y over that? And just 1. So in other words, this kind of looks like x over z, y over z, and 1. Whereas if I did the bottom, then I could solve for z, I would get the negative radical. Applying that same formula, say minus fx minus fy, positive 1. In this case, I would get the negative of x over this, comma the negative of y over this, comma 1. But notice that I can also think of that as x over z, y over z, and 1. Do you notice that? Because here the z has the negative sign in it, here it didn't. So it kind of looks like the top and the bottom are almost the same, except in this one, my denominator is always going to be positive, while in that one, the denominator is always going to be negative. So there is some sort of sign change here. So this gives us the idea of a radial vector. So what we can do here, to deal with both the top and the bottom at the same time, it's another easy parameterization, and it doesn't work for every surface, but a sphere is a nice surface to do it on. We can sort of scale by z. So that's sort of, I know we usually scale by a constant, but we'll take this idea of scaling
Wait,
by z.
that's supposed to be negative, those, right?
No,
No.
because here the z is
Oh,
negative.
it's,
And so if I multiply these guys through by z, I'll get sort of the same thing. So I'll get my normal to look like x comma y comma z. And so now, the sign change is kind of happening for me, because whenever my z is on, whenever I'm in the upper hemisphere, this is outputting a positive number. If I'm in the lower hemisphere, this is outputting a negative number. So the normal is sort of self-orienting. So this guy here, and it's kind of because the sphere behaves very nicely, the radius is proportional. We'll talk about that later, but this is called the radial vector.
Professor, what do
Yeah.
you mean like scale by z? Like how do you find?
Scale means you multiply a vector by something.
anything like.
No, I divided by z here, so I just multiply by z to clear the denominator.
Okay.
If I multiply this by z, I get that. But also if I multiply this by z, I get that. And this guy, it has the sign change built into it. So whenever I'm in the upper hemisphere, the third coordinate is positive. If I'm in the lower hemisphere, the third coordinate is negative. So this is called a radial vector. It's basically that vector that gives you the radius of a sphere. So if you're on a sphere, the vector that points out to the radius is always going to be the vector x comma y comma z. So that's a nice concept we can take advantage of when we're doing a sphere. That's always going to be your normal vector. And then we can kind of scale it. There are some applications in which this is kind of weird to apply, but in general, that's a normal vector for a sphere. We'll stop there and we'll do more next time. The next time we'll talk about surface integrals and maybe do some more area problems. But really start thinking about finding normal vectors and knowing which one's the right one and knowing what's the best way to approach the situation. That's going to be important.